how the glass door knows when to open, how a weighing scale measures the weight, how an air conditioner or a refrigerator knows exact environment temperature, how a car knows their tire air pressure, how a water tap knows when to turn on, how a room cleaning robot or an AGV knows where to move. Hi there, this is Ayush from Master Mechatronics today, and welcome you to the brand new series on sensor and their selections. In this series, we will understand the selection and working of all type of sensors used in factory automation. Now, if you are a beginner mechanical engineer or still studying in college, you might be wondering that the sensors are basically electrical and electronics device, right? Their working, wiring, programming all falls under electrical engineering. So why should we as a mechanical engineer need to understand sensors, and what exactly we need to understand about the sensor? So I would say if your work is only limited to core mechanical design like fixture designs, BIW body in white design, or a specific product design, then you don't need to go too deep into sensors. Just knowing the basics like which type of sensors is used where is enough. But if your work involves designing automatic machines like assembly lines, process machines, packaging machines, or robotic equipments, then that's a different story. For me, as a special purpose machine design engineer, SPM design engineer, my work is to designing the industrial machines which work automatically, fully automatically. When operator press the start buttons, the entire machine has to perform all the operation automatically. And it's not possible without sensors. So first off, if your work is designing automatic machines, then you are not a mechanical design engineer anymore. You are actually a mechatronics design engineer. And to become a truly good automation machine design engineer, you must understand sensors beyond just their name. You need to understand the every parameters of the sensor data sheet, their design, type, working principle, circuit, accuracy, list count, even the price range. Only then you can confidently select the right sensor, the exact model number as per your machine requirement. Let's take a practical example to understand it better. Suppose we have a bearing that need to be press fitted into this housing like this. And to do that, I have designed a small setup using a hydraulic press, a fixer to properly locate the housing, and a pressing tool to hold the bearing. Maybe with a magnet, you can also use the ball catcher to hold the bearing. Now, in any automated assembly machines, before actual operation starts, the machine first checks whether all parts are properly placed. Because if any part is missing, it can damage the machine tool, the fixture, or the top tool, or maybe it could damage the child part. Or maybe product will get assembled but without some part, without some missing parts, which we don't want at any cost. So to make sure that all child parts are present and correctly positioned, we use part present sensors, or we call it job sensor. These can be a contact type switch, limit switches, or non-contact sensor like proximity or photoelectric sensor. In this setup, the housing is metallic, so we will use inductive proximity sensor to detect it. And for bearing, since we cannot place the sensor too close, a photoelectric sensor would be better. It can detect from a distance. So when the operator loads the both components, these sensor detects their presence and send a signal to PLC or controller confirming that the machine is ready to start. Now, here comes to the important part, the press fit quality. So, the fitment of bearing inside the housing depending on interference between the bearing's outer diameter and the housing bore. If the interference is too small or negative, bearing will be loose. Or if it's too high, the bearing or housing might get damaged during the pressing. So, how we can check if interference is correct? So, we can install a force sensor, usually a load cell, above the pressing tool to measure the pressing force. A load cell measures the static or slow changing force acting on it. Let's say the pressing force for a good fit should be between 500 kgf to 1 ton. That range can be defined by trials or calculation. So during operation, if the measured force goes below that range, it means the interference is less, the bearing will lose. If the force goes above the range, the interference is too high, the part could get damaged. And this is how, using a load cell, we can ensure the interference fitment quality of the product. And since this is a hydraulic press, we also need to consider operator safety. For that, we can install a safety curtain sensor, also known as area sensor, which stops the press immediately if anything enters into the working area. So, as we have seen, to check the presence of component, we use detection sensors like inductive or photoelectric sensor, which helps to confirm that all child parts are loaded properly before the machine operates. And to measure the pressing force, we used load cell sensor, which helps ensure the fitment quality of the bearing. And to make the machine safe to operate, we used safety curtain sensor. So sensors are not only automate the process, it's also ensure the quality of the product and also make the machine safer to use. For a general mechanical engineer, this level of understanding, knowing what a sensor does, which sensor is used for which application, is usually enough. But if your job is to designing automation machines, your job is even deeper. For example, here we have used a force sensor, a load cell. But which type of force sensor should we actually use? There are button type, pancake type, S-type, beam type, and each is designed for different loading condition. If the load is 20 ton, we will need one type of sensor. But if the load is 20 kilogram, we need a completely different one. And choosing a sensor is not only about rated load, it's also about required accuracy. We must understand what accuracy class we need and what list count we will get after analog data is converted into a result by the control system. Then comes to another question. For our application, should we use a strain gauge type load cell or a piezoelectric type? Which one performs better for a static condition and which one is for dynamic loading? And the same thing goes for detection sensor. Take the photoelectric sensor. There are the different types: diffuse, retroreflective, through beam. Each one works best for a specific case. Then there is a different light source, LED, laser, or fiber optics. And we have to also decide whether to use a PNP or NPN type sensor. Each variations are made for a specific purpose. Some performs better when part is bright, some when the part is dark, some for the long distance, some for the shorter one, and some for the very short one. As a mechanical engineer, we must be able to select the right sensor based on the machine function and the requirement. Now, the real problem with most of us as a mechanical engineer is we actually understand the sensor's logical part, but we lost when it comes to electrical part. For example, we know how the load cell works. We understand that it uses a strain gauge that changes resistance with applied load. But what happens after that? How does the small change in a strain gauge actually converts in voltage or current? And then what is the role of load cell controller? And then how does the PLC process the signal and convert back into kilogram or Newton? We often stop here. We think it's an electrical engineering part, programming part. But for us, it's important to know at least the basic, because this understanding defines the sensor accuracy, errors, least count that we get in final result. And the same thing happens with digital sensors. We understand how a photoelectric sensor detects an object when a light beam between transmitter and receiver is interrupted. But when it comes to PNP and NPN sensor, what does mean how they generates the output signal? We lost the link. So to truly understand the sensors, we have to study both the logical working and the electrical processes behind it. You can't understand fully one without another. And this is exactly what we are going to learn in this very first lesson, that how a sensor actually works. And once you understand this foundation, then fully understanding any sensor will become much easier. Because at the end, any sensors works in only just two ways. Either as an analog sensor, like force sensor, torque sensor, pressure transducer, linear potentiometer, or an encoder, or as a digital sensor like proximity or photoelectric sensor. And in this video, we are going to master the both type of sensors. So let's start from very basic. What is a sensor? So there are many definitions out there from different sources. As per automation industries, for example, as per Kens, which is a well-known Japanese brand in sensors, sensors are used to detect, measure, or inspect a target during a process to increase efficiency. Omron, another well-known Japanese sensor manufacturer, define it as a sensor is an element that converts external energy, physical quantity, or information, etc. into electrical signal by scientific means. So you can see the industrial definition mainly focus on sensor as an element using for detecting a target or measuring a physical quantity and then convert it into electrical signal to automate the machine and improve efficiency. Now, if you understand from the general engineering point of view, a sensor is a device that detects an object or measure of physical properties like force, temperature, light, motion, pressure, etc. and then convert it into a signal that can be read, displayed, or processed. That means sensor doesn't have to always give an electrical signal. Even it doesn't have to be an electronics device. For example, take a pressure gauge. It's measure the fluid pressure, air or liquid, and show it directly on dial. There's no electrical signal. Here it's pure mechanical, but still as per definition, it's also a sensor because it converts a physical quantity, that is pressure, into a readable signal that can be interpreted. However, in this series, we will focus only on industrial automation sensor. So we can think of the sensor as an input device, a device that detects or measures a change in physical quantities and give a signal in form of voltage or current, which can be read by the automation system like a PLC. Basically, sensor acts like a bridge between the physical world and the electrical control system of the machine. Now, some of you might be thinking, wait, aren't sensor and transducers the same thing? So yes, every sensor is a transducer because a sensor also converts one form of energy into another, just like a transducer does. For example, a thermocouple, which is a temperature sensor, converts heat energy into electrical voltage that can be measured or displayed. But all transducers are not sensor. For example, a loudspeaker, it's convert the electrical energy into sound energy, convert one form of energy into another, but it's not measuring or detecting anything. So let's make it a transducer but not a sensor. So this is the basic definition of a sensor, a device that detects or measures a physical quantity and convert it into a signal that can be displayed, processed, or used for the automation. Now let's understand how any sensor actually works. So every sensor is made of three basic components. One is sensing element, a transduction element, and a signal conditioning unit. The sensing element of the sensor is the part of sensor that actually interact with the physical world. For example, in load cell, the metal body that directly takes the load is the sensing element. In thermocouple, the metal junction that comes in contact with the temperature source is the sensing element. In photoelectric sensor, the light beam or the LED that emits the light is the sensing element because that's what interacts with the object through the light. In inductive proximity sensor, the inductive coil is the sensing element. It generates an electromagnetic field. When a metal or object enter into the field, the sensor detects it. Now, the output from the sensing element goes into transduction element, which is the second most important part of sensor. The transduction element job is to convert the physical changes detected by the sensing element into an analog electrical signal, that is a continuous variable voltage or current. Let's take the example of load cell again. So inside the metal body, there are strain gauge foil bonded with the surface. When the load is applied, the metal body deforms slightly in micron, and that tiny deformation causes the strain gauge to stretch or compress. Now, as we all know, the electrical resistance of a wire depends on its length and the cross-section area. So it's increased when wire is stretched, reduce its cross-section area, and decrease when it's compressed, cross-section area increase slightly. So as the strain gauge stretch or compress, their resistance change. These strain gauges are connected in a Wheatstone bridge circuit, which converts this very small change in resistance into a measurable voltage difference. So this combination of a strain gauge and Wheatstone bridge forms transduction element of the load cell. It converts the mechanical force into analog electrical voltage, and higher the load, the greater the voltage difference. Now let's take another example, a photoelectric sensor. Here light is emitted from an emitter, usually an LED or a laser source, and it's received on photodiode or phototransistor at the receiver side. In diffuse type sensor, the receiver is inbuilt in same housing, but in through beam it's placed separately, which we will discuss in detail in next video. Now, if you remember, the light always carries an energy in form of photons. And when the light falls on photodiode or phototransistor, these semiconductor materials converts the light photon energy into electrical energy, producing a small current called photocurrent. That's the transduction process of a photoelectric sensor, converting the light energy into electrical energy. The amount of current depends on how much light reaches the receiver. So when an object comes in front of the beam or block the light, the received light and therefore the photocurrent drops suddenly. That sudden voltage change is what makes the sensor to detect the object. But the problem is the analog signal coming from the sensor's transduction element are often very weak, unstable, and raw. They are usually in millivolt or even in microvolt range, and the current can be low as few microampere. For example, a load cell gives around 1 to 30 millivolt of raw output. Similarly, in photoelectric sensor that use a photodiode, The output current is typically range of 1 microampere to 100 microampere, and the voltage developed across it will be just few millivolt or few hundred millivolts. These signals are so weak that they easily get disturbed by the electromagnetic noises coming from nearby motors, drivers, or other electrical components. As a result, we get fluctuating or unstable readings. But a typical control system like a PLC expect a stable signal in a standard range for analog 0 to 10 volt or 4 to 20 milliampere, and for digital signal 0 and 24 volt. So to make these weak signal usable, we use a signal conditioning unit, the third major element of any sensor. Now, before we continue, a quick note for mechanical design engineers. Many times we have to design enclosure for electronics or PCB boards. Making these in plastic molding or sheet metal becomes complicated, time consuming, and often the fitment is not perfect. So to solve this problem, our today video sponsor JLCMC has launched a wide range of custom aluminum enclosures for electronics. These are fully customizable, size, colors, drillings, laser marking, and even extra machinings. They also provides an online customization interface so you can clearly see your requirements. The enclosures offers industrial grade protection, good heat dissipation, and strong EMI shielding with strict quality control. But the main deal is price and the lead time. You get instant online quote, no mold cost, and much faster delivery compared to traditional methods. If you don't know JLCMC, so they bridge the gap between high cost and high quality in mechanical components. They deliver precision linear motions, transmissions, pneumatics, you can name it. And now this custom aluminum enclosures. So it's time to redefine your enclosure designs. Head to JLCMC to get the perfect enclosure that meet your specification with better cost. Link is in description. Now let's continue to the topic. A signal conditioning unit performs several important functions. First is amplification. It's amplify the weak analog signal from the transduction unit to a usable level. Second is filtration. The signal may contain noise due to electrical interferences, vibration, or light flicker in case of optical sensors. Filters like low pass or band pass circuits remove these noises and smooth the signal. So only useful parts remains. Third is linearization. Many sensors such as thermocouple or RTDs don't have perfectly linear response. The conditioning circuits correct this non-linearity, so the output becomes directly proportional to the measured quantities. Then the offset and scaling. It adjusts the baseline, zero correction, and set the full scale range. So the signal fits into a standard output range like 0 to 10 volt or 4 to 20 milliampere. And least but not last is isolation. It's protect the control system like PLC from a high voltage, spikes or ground loops coming from the sensor side. Now, if you have noticed, I have keep repeating one thing. The transduction element of every sensors always gives analog output, even for those sensors which gives finally digital signals. Let's take photoelectric sensor example again. So the amount of photocurrent produced depends on how much light receiver gets. If the target is white and bright, about 90% of light is reflected. So the receiver gets full light and the output might be around 100 millivolt. If the target is gray, maybe only 50% of light reflects. So the signal drops to around 50 millivolt. If the target is black, almost all light absorbed, the reflected light is very low and the output might be just 5 or 6 millivolt. You can even see this effect in sensor datasheet, where they mentioned how the color or brightness of the targets affects the sensing distance. So internally, the signal is not clean on or off. It's a variable analog signal that continuously changes depends on how much light is received. But in industrial application, we don't want variable signal from such sensors. We want sharp digital output. If object is present, it should give 24 volt, not 5 volt, not 10 volt, it should give 24 volt. If not, it should be 0 volt, not 5 volt, not 10 volt, 0 volt. Yeah, if the sensor is normally open type, then it will reverse, but only either 0 or 24. So apart from amplification and filtration, the signal conditioning unit in digital sensors do one more important task. It converts the analog signal from the transduction element into digital signal, that is 0 or 24 volt. Whereas in analog output sensors like Loadcell, linear potentiometer or pressure transducer, the signal conditioning unit scale the weak analog signal output into a standard voltage range. So a control system like PLC can process it properly. So first let's understand how a signal conditioning units work for the analog output sensor, how it scales the weak signal into voltage or current, and how the PLC read the signal and convert it into physical unit like kilogram, newton, or like for potentiometer, how it converts into millimeter. And then we will understand the signal conditioning units for the digital sensors like proximity sensor and photoelectric sensor. And then finally, we will go deeper into their two operating type of digital sensor, PNP and NPN. So let's start from very basic question. What is an analog signal? An analog signal is a continuous electrical signal whose value changes smoothly with the physical quantities being measured. For example, in a load cell, as the load increases, the output voltage of load cell also increases smoothly. That's why it's called analog, because it's changed continuously, unlike digital signal. Now, when we talk about analog signal, we often see two types of output. Some sensors gives output in voltage like 0 to 10 volt, 0 to 5 volt or 0 to 30 volt, and some sensor gives output in current, typically 4 to 20 milliampere. So the question is, why do some sensors gives their output in voltage and some sensors gives in current? Are they not interchangeable? Because we know V equal to IR. That means if there's a current, there must be a voltage difference. And if there is a voltage, there must be some current flow. So yes, almost every sensor initially generates a voltage signals inside. Because most transduction elements like strain gauge, thermocouple or photodiode work by producing a change in voltage or resistance. But what finally comes out from the sensor and goes to the PLC or the controllers, depending entirely on signal conditioning unit of the sensor. Both current and voltage both carrying the same information, only the form of electrical signal is different. Now let's see when we should use which. So if the distance between the sensor and controller is short, let's say less than 10 meter, we can easily use voltage output sensor like 0 to 10 volt. It's simple to wire and easy to measure. But if the distance is long or if the environment has electrical noises, then prefer a current output sensor, typically 4 to 20 milliampere. Because the current signals are not affected by the voltage drop in wires. Also, they are much more immune to the electrical interferences, electrical noises. Now, there is another big advantage of the current output. In 4 to 20 milliampere loop, the signal never starts at 0. It starts with 4 milliampere, which represents the minimum zero load condition. So if you ever see 0 milliampere, it usually means wire is broken or sensor has failed. That's a built-in safety check, something that you don't get with 0 to 10 volt signal, because 0 volt could be either means no load or broken wire, and you cannot be sure which one. That's why in critical or safety related application, we prefer current output sensor. So should we always choose current output sensors? Not really, because current output sensors are usually expensive. So we should use the current output sensors only when the sensor cable length is more than 10 meter, the environment is electrically noisy, or accuracy and reliability are critical. Otherwise, mostly in factory automation, we use voltage output sensors. 0 to 10 volt for analog signal, 0 to 24 volt for digital signal. Now, we have to also understand that not every PLC can accept the voltage and current port type of inputs. So always check what your PLC input channels are designed for before deciding the which type of sensor output you want to use. Now, here is a twist. The PLC do not understand the current or voltage signal directly. PLC only understand digital numbers. So we need a device that converts the analog signal, either the voltage or current, from the sensors into a digital number for the PLC. That device is called ADC, analog to digital converter. In PLC system, we generally call it analog input module. It can be inbuilt in PLC depending on the model or add as a separate module. If you have two analog inputs, you will need two separate input channel or module to read them. So now let's understand how an analog input modules converts the voltage or current output from the sensors into a digital numbers, and then how we finally get the results in our physical units. So suppose we have a load cell of 500 kg capacity with sensitivity of 2 millivolt per volt. That means if we supply 10 volt of excitation to the load cell, then at the full load 500 kg, the bridge output will be 2 millivolt into 10 volt, 20 millivolt. So the full scale raw signal from the load cell is just 20 millivolt, and PLC cannot read this directly. So the 20 millivolt first goes into a load cell controller, the signal conditioning unit. This amplifier increases the weak 20 millivolt signal to a standard voltage range, typically 0 to 10 volt or 4 to 20 milliampere. So now when the load cell has no load, sensor final output is 0 volt. And when it's loaded with 500 kg, the final output will be 10 volt. If it's a current output sensor, it will be 4 milliampere at no load and 20 milliampere at full load. Now the signal is strong enough to send to the PLC. But again, as I said, the PLC doesn't understand voltage or current directly. It's only understand digital integers number. And the bit size of the PLC decide how many digital counts are available. For example, Mitsubishi PLC often use 12-bit ADC, which means 2 upon 12 4096 counts, whereas Siemens PLC typically use 15-bit, which gives us 32,768 count. You can also check your PLC datasheet, most are between 12 to 16 bits. However, not all counts are used for measurement signals. Some are reserved for overrange or diagnosis function. So practically in Siemens PLC, you will get around 27648 counts. In Mitsubishi PLC, about 4000 counts. Let's continue this example with Mitsubishi PLC. So the analog input modules scale the range of 0 to 10 volt or 4 to 20 milliampere to 0 to 4000 counts. That means 0 volts or 4 milliampere equal to 0 counts. 10 volt or 20 milliampere equal to 4000 counts. You can also configure this scale as you want. For example, if you set 5 volt as a full scale, then 0 volt is 0 count and 5 volt is 4000 count. But for now, let's keep 10 volt equals 4000 counts. So every voltage levels between 0 to 10 volt is converted proportionally into digital numbers. Now, since 10 volt equal to 500 kg, the scaling inside the PLC is simple. The digital count equal to measured load divided by the full scale load, which is 500 kg in this case, into full scale count 4000. So if the load is 100 kg, the digital count will be 800. If the load is 200 kg, the digital count will be 1600. Now let's calculate the resolution or least count of the system. So we are scaling 4000 counts to 500 kg. That means the one count equal to 500 divided by 4000, 0.125 kg, 125 gram. So even if the load cell can measure 100 grams or 50 grams, the system can only display in a step of 125 grams. Because that's the resolution limitation of your PLC input system. And this same calculation method applied to other analog sensors like linear potentiometer or temperature sensor. So here is a quick question for you. Suppose we have a linear potentiometer, not an LVDT, with a 100 millimeter stroke length. And we are using the same PLC and analog input module. So what will be the digital list count of the potentiometer? You can let me know in comment. So this was all about how our analog output sensors works from a weak signal to a digital numbers to a physical unit. Now let's move to digital output sensors. But before that, what exactly is digital signal? So a digital signal is signal that has only two possible states, either on or off, or we say high or low, or 1 or 0. Unlike an analog signal which change continuously between two limits, a digital signal only switch between these two distinct levels. It's just like a simple switch. That's why digital output sensors are also called as switching sensor. It's less about the level of voltage or current output. It's more about the logic. Now, why do we need the digital output sensors? So in many applications, we don't want to measure something, how much something is. We just want to know that whether it's there or not. For example, in part detection, we just want to confirm if the part is there. In counting applications, we just need a pulse for each item. In position confirmation, we just need to know if the position is reached or not. In all these cases, we just want to know yes or no, on or off information. That's exactly where digital output sensors are used. Now, as I said earlier, all the sensors, digital or analog, initially generate analog signals inside, because the sensing element always produces a variable output. So how do we get digital on-off output from it? So at first I was used to think maybe a digital sensors like photoelectric sensors are also first convert the analog signal into a standard 0 to 10 volt range, and then PLC set a threshold. Like if signal is between 5 to 10 volt, call it on, and if it's between 0 to 5 volt, call it off. But that's not how it actually works. And there are some practical reasons for that. If we use that method, it would make the circuit more complex and expensive, because we would need a full analog conditioning circuit and an analog input module in PLC. Also, it would make the response slower and less stable. That's why the digital output sensors are designed differently. They use a very simple internal circuit, usually a 3-wire configuration. So let's understand how the internal circuits inside the digital output sensors actually works. And let's understand it with a practical example of a photoelectric diffuse type sensor. So a diffuse photoelectric sensor mainly has two sensing parts. One is light emitting LED and one is light receiving photodiode or phototransistor. When no object is in front, the LED light do not reflect back, so the receiver gets almost no light. But when an object comes in front, the emitted light reflected from the surface and return to the receiver. The photodiode then generates a tiny photocurrent proportional to the receiving light. This current is extremely small, usually in microampere range. So the first circuit inside the sensor is amplifier circuit. The amplifier increases the signal strength to few hundred millivolts. But it's still an analog signal and it's still fluctuate with the light intensity, object color and distance. So to make it useful, we use a signal conditioning unit, which can be built either into the sensor body or placed externally as a small module. Normally, it's often built-in sensor body, but in compact sensors for tight mounting space, the amplifier or adjusted units keep separate. So you can do the settings like range or sensitivity easily from the panel. Now, in a digital output sensor, the signal conditioning unit generally has two main parts. One is comparator circuit and another is output transistor, either PNP or NPN type. A comparator acts like an electronics decision maker. It's compare the amplified analog voltage from the sensing elements with a fixed reference voltage. And that reference value can usually be adjusted either through a mechanical means or through programming. If the signal from the photodiode is greater than reference, the comparator output goes high, means object is detected. If the signal is low, it goes low, means no object is detected. So technically, the comparator converts the analog signal from the sensor sensing unit into digital one. But this digital signal is still very small, only a few microampere of current or around 5 volt or less. It's not enough strong to drive a long wire or PLC input directly. That's where the output transistors comes in. The output transistor is basically a small electronic switch made using semiconductor materials. It can be PNP or NPN type. A transistor in normal conditions behaves like an insulator, no current flowing through. But when a small current is supplied to its base in certain way, it becomes a conductor and allowing the current to flow between its emitter and collector. So you can think of it's a switch that controls the 24 volt output signal using a small control current. If you want to understand the transistor operation in detail, I have added a separate video, link is in description. For now, just remember the comparator decides when to switch and the output transistor perform actual switching of the 24 volt signal. Special things about transistors as a switch is it's on and off in milliseconds. It's extremely fast and reliable. It can run for millions of cycles. Because there is no moving parts, it's a solid state switch. Now, to understand which type of transistor output we should choose, PNP or NPN, we need to understand how they wired and how the current flow differently. And this is usually the parts that confuse most of mechanical engineers. So let's go step by step from completely basic. How does any electrical or electronics component operates? Simply when electric current flow through it, right? And the current only flow when there's a complete circuit and a voltage difference. For example, if we have a bulb and a battery, to turn on the bulb, we connect one terminal of batteries to 24 volt and another terminal to the 0 volt. Now the circuit is completed, current flowing and the bulb lights up. Now, if the both sides are connected to 24 volts, there's no voltage difference, no current flows, so the bulb will stay off. Now, if the circuit is open, again no current, bulb off. The same concept applies to sensor and PLC wiring too. Industrial sensors and PLC operates at 24 volt DC. That's why every control panel has a DC power supply, which converts the AC current into a stable 24 volt DC, sometimes 5 volt or 10 volts if required. You can think of it just like a battery, 24 volt as positive or high, and the 0 volt as a negative, ground or common. All means the same. Now let's see how we wire the components. So there are two main types of wiring in panels, the power wiring and the signal wiring. Every device includes PLC gets its own power wiring. It's positive 24 volt and the ground 0 volt connected to power supply. And a typical digital output sensors like photoelectric sensor or proximity sensor has three wires. Brown for 24 volt DC, blue 0 volt to be ground, and black the signal output. We connect the brown wire to 24 volt, the blue wire to 0 volt, and the black wire, the signal output, goes to the PLC input terminal. But at this point, the signal circuit is still not complete, and how it's completed depends on the type of output transistor in sensor, whether it's a PNP or NPN. So let's zoom in into sensor internal circuit. Inside, the 24 volt power continuously runs the sensing circuit, the LED, the amplifier, the comparator, and the transistor stage driver. This part of circuit is always powered and ready. Now, depending on whether the output transistor is PNP or NPN, the signal circuit changes. So now let's understand how the signal circuits works. Starting with PNP type transistor. In PNP transistor, the emitter is connected to positive voltage, usually 24 volt, and the collector is connected towards the ground side. The base terminal is connected to internal control circuit called stage driver, which is controlled by the small digital signal coming from the comparator. In normal condition, when no object is detected, the comparator output remains low. And in this condition, no output current is sent to the PLC input. But when the objects come in front of sensor, the light from the LED reflects back to the receiver. The photocurrent increases and the comparator output goes high. This signal from the comparator activates the internal drive circuit, which slightly pulls down the voltage of the transistor's base, about 0.7 volts lower than the emitter voltage. So if the emitter is at 24 volt, so the base becomes lower than 23.3 volt. And when this happens, the transistor turns on, allowing the current flow from the emitter to the collector. So the 24 volt from the power supply flows through the emitter, through the transistor, coming out from the output wire, which is the black wire connected to the PLC input. But nothing happens. Why? Because current only flows when circuit is completed. PLC internal inputs terminals are connected to 0 volt, ground, internally. Of course, this has some electronics, but it's make a complete circuit. So the current flows from the sensor 24 volt output into the PLC input terminals and return through the PLC 0 volt line. PLC then registers the current is flow as a high signal. And this is how the PNP sensors works. It's sourcing the current to the PLC input, means it's provide the 24 volt when the sensor output is active. Now let's take the NPN type sensor, which has an NPN output transistor. So its work almost same as PNP sensor, but the current flows in opposite direction. In NPN transistor, the emitter is connected to 0 volt, the ground side of the power supply, and the collector is connected to the output wire, the black wire, which goes into PLC input. Inside the PLC, the input terminals are internally connected to 24 volt. So the collector side of transistor always stay at high potential, 24 volt, while the emitter side stay at 0 volt. But nothing happens because circuit is not completed. Signal cannot flow in circuit. And same, the base of transistor is connected to internal drive circuit, which is controlled by the sensor comparator output. Similar to the PNP type but in reverse way. In PNP transistors, the transistor turns on when its base is made lower than the emitter by about 0.7 volts. We were pulling out the current from the base. But in NPN transistor, it's opposite. The transistor turns on when the base is made slightly higher in voltage than the emitter. We supply the current into the base instead of pulling it out. So when an object comes in front of NPN sensor, the comparator output goes high, and the internal circuit sends a small current to the transistor base, which slightly increases the base voltage, and this turns the transistor on. Once the transistor on, the current doesn't go out of the sensor as it did in PNP. Instead, it flows in opposite direction because the current always flows from high voltage to the low voltage. From the power supply 24 volt through the PLC input terminal into the sensor output, the collector through the transistor, and finally go back to the 0 volt. That's the complete circuit. So the PLC detects this current flow and read as an on signal. Because here the current flows from the PLC to the sensor, we say the sensor is sinking current from the PLC input. That's why NPN sensors are also called sink-in type output. In contrast, the PNP were sourcing type because they pushes the current into the PLC input. But in both of cases, there is a one key point that anything to work in electrical system, the circuit must be completed, otherwise current won't flow through. And here is something very important. Let's say you have a NPN sensor, but your PLC input module is designed for PNP sensors. Means its inputs are internally connected to 0 volt, not 24 volt. So in that case, even if the PNP sensor transistor turns on, no current will flow because there is no voltage difference between two sides of the circuit. So whenever you select a sensor, always check what kind of input your PLC supports, PNP or NPN. Some PLC comes with universal inputs. It can accept the both, but it's usually more expensive. So which type of sensor output we should select? So first off, both type of sensor output, NPN and PNP, are widely used worldwide. But among them, PNP type output is mostly used, especially in Europe, India, and most modern global automation system. And there are few very clear reasons for that. In PNP sensor, the output goes high 24 volt when active. So even if the output wire accidentally touches the ground, it won't create a false signal or damage the circuit. Second is easier to troubleshooting. You can simply measure the output wire with a millimeter. If it shows 24 volts, you immediately know the sensor is on. Third is positive logic. PNP sensor matches the common logic used in most control systems today, which is 1 means on and 0 means off. NPN sensor, the sinking type sensors, are still common use in Japan. That's because Japanese automation industry historically developed using NPN transistor in their output circuits. Also, the NPN transistors are slightly faster than PNP transistor, so in high-speed application, they can offer a minor advantage. And from a manufacturing point of view, NPN transistors are cheaper to fabricate than PNP one. But globally, the PNP sensor have now become the standard. But still, as a design engineer, we should always check the PLC and the control panel before selecting a sensor, whether it's supporting NPN or the PNP signal inputs. Now, in some machines, we need more information from a sensor than just on or off. For example, not only to know if a part is present, but also how far it is, how strong the reflection is, what the temperature inside the sensor is, or even to diagnose the sensor. Is it working properly or need cleaning? Then a normal sensor cannot do that. They just give 0 or 24-volt output signal. That's where the smart sensor with IO link communications comes in. And IO link sensors still use the same standard 3-wire connection. But instead of it just on and off signal, it can communicate full digital data with the controller. Through the IO link, the PLC can read real-time parameters like setting the sensor range, monitor internal diagnostics, and even changing the sensor setting remotely, all through the software. This helps in preventive maintenance, reduce downtime, and allow the complete machine transparency right from the control panel. So when your machines require more than just detection, when you need data, not just signal, that's where a smart sensor is used. So this was all about the basics of sensors, their wiring, connection, and the working. I know the electrical diagrams was not as per the standard. I was used to represent just the concept. So if you are electrical engineers, you know the better. Here I just try to explain the core concepts. I hope this video will help you to understand the basic working of analog and digital sensors. So the next video, the detection sensor, should be on your screen. And thank you so much for watching this video.